5 transponders at each end. Well, based on that capacity scaling, next year you're going to need to add a little bit more than double those amount of transponders. And in a few years, about 5-6 times that. And within a decade, you're going to be essentially deploying 100 times as many transponders at each node in the network each year, not just total cumulative, but each year. And so how do you do that effectively in terms of space and power utilization? So essentially the bottom line is, with current technology of 10 gigs per line card, where operators today are deploying on a typical number of transponders per year per network, they're deploying several thousands per year to scale their nationwide US backbone networks. Well, as you scale that to the capacity requirements that are forecast at 10 gigs, the model just breaks. You're going to need 100 times as many work orders and truck rolls each year. Even if you move to 40 gig line cards or 100 gig line cards, you're making a dent, but you're still scaling by factors of greater than 10 in all of your OpEx costs. And so, you just can't scale the network that way. So one way that to change the paradigm, and this is what Infinera is doing, is leveraging photonic integration. So taking all of these components that go into these discrete 10 gigabit or 40 gigabit line cards and integrating them onto a pair of photonic integrated circuits. So this is literally doing what was done 40, 50 years ago by Fairchild Semiconductor when they invented the first silicon IC. Take hundreds of optical components and put them onto one photonic chip, all monolithically integrated. And with that, you significantly reduce all of the space, power, fiber coupling, and so on required to build these optical transport systems. So right now we've got 100 gigabits per photonic chip. So that means you've got one circuit pack that's outputting 100 gigs per chip, compared to the state-of-the-art really being 40 gigs per chip at best, and prevalently more than 10 gigs per chip with most commercial technology that's widely deployed. And with that, we're looking to scale that. In a couple of years, we're going to do 400 gigabits per chip, and after that, follow it up with about 1 terabits per chip. And then we see a roadmap to be able to scale that, sort of bringing an optical Moore's law to the industry into the several terabits of photonic capacity per chip. And fundamentally, the industry needs that. You need to be able to deploy 10 times, and 50 times, and 100 times the capacity without having to scale all of your physical space and power infrastructure that goes behind that. So, what that does is it does keep things in the range of manageability. It allows service providers to scale network capacity without having to ridiculously scale the number of circuit packs and line cards they need to deploy each year, and the amount of space and power that those are going to consume along with that as well. So an interesting report from Heavy Reading, this market research firm that tracks a lot of the technologies and trends in the optical networking industry. They did a very interesting report on photonic integration earlier this year. And their conclusion was that photonic integration really is the best hope for the optical industry to be able to scale to meet the needs of the underlying capacity and bandwidth requirements that are coming at us. So the way that you can use photonic integration is to use these digital chips inside your optical transport systems. And essentially you use them to take the optics out of your optical network. Essentially you use them to reconvert at every node all of this photonic capacity on multiple wavelengths back into the digital domain. And with that, you can bring a lot more feature functionality back into the optical network. You can bandwidth manage the capacity in the digital domain. So you can groom out packet streams or circuit streams if you're bandwidth managing 2.5 or 10 gig circuits. And with that, you can also take out all of the coupling of optics with services. So in other words, you can regenerate and restart that photonic signal at every node in the network. So therefore, you're not having to consider things like wavelength blocking and optical reach and dispersion and so on, where you're trying to turn up the 10 gig or 40 gig circuits in your network. And really that enables operators deploy what's called a digital optical network. So essentially decouple service provisioning from the optical engineering, use protocols like GMPLS software intelligence to literally allow new transport circuits to be deployed end-to-end just with point-to-point provisioning requests in a matter of minutes. So that from a technology perspective absolutely is feasible. And in fact, deploying bandwidth in chunks of 100 gigs or eventually 400 gig or terabits through photonic integrated circuits means you have that pre-deployed capacity that's there, and then you can start leveraging these protocols to automate all of that bandwidth delivery. And then, obviously the digital switching at 3 enables that. I'll skip this for the purposes of time, just showing that essentially you can now start treating bandwidth or transport capacity really as a pool of bandwidth. When you've got new service requests, you just take away from that pool. You don't have to be individually looking at specific wavelengths and measuring PMD and chromatic dispersion on fiber and figuring out whether you've got wavelength blocking. It's issues like that that lead to 30-day and 60-day delivery intervals, because essentially a new service request is a detailed optical planning and engineering activity with service providers. So what that enables is a programmable optical network. Essentially, you have a PIC-based optical engine that delivers the bandwidth, whether it's 100 gig PICs or 400 gig PICs, and using optical tools like Raman amplification and chromatic dispersion compensation and so on to get you between points. But you want to virtualize all of that and bring in a layer of software to essentially then just allow users to connect with whatever port they want, whether it's a gigabit Ethernet, 10 gigabit Ethernet. Very soon it's going to be 100 gigabit Ethernet. There was a demo last week at NextCom in Las Vegas where EXO carried a 100 gigabit Ethernet pre-standardized circuit across their network, terminating at NextCom in the convention center. And then you leverage as much network intelligence as possible, protocols like GMPLS to automate a lot of the service provisioning. So, the exact rate of growth of the internet is hard to measure in terms of where and how much, and variations by week, by day, by minutes, by service provider. But we definitely know it's growing fast. The discussion of who the users are of all this bandwidth and video, absolutely, it's people that are way younger than us, and they're just, my kids got an iMac, they're watching all their Star Wars and stuff on YouTube now. They don't even watch TV half the time. So there's definitely going to be more and more of that. As soon as all these low quality video apps start becoming high definition, those TV boxes are going to become obsolete pretty quickly, because there's going to be so much content that's going to be delivered on the internet. So what we do know though is that some of these traditional optical paradigms just aren't going to be able to scale. Scaling, the bit rate of each wavelength is really the only metric by which you measure progression in the optical layer. Just isn't going to scale. You've got 40 gig waves today, you might have 100 gig waves. In a couple of years, you're not going to have terabit waves. It's just beyond the possibility of physics to get there. So how do you scale that bandwidth capacity, not just in terms of bit rate per wavelength, but also around the metrics that matter, space and power consumption as well, to save CapEx as well as OpEx. So just a few sort of ideas, data points to throw out there. Hopefully this gets you thinking around things. I'd like to open it up to any questions that you might have.